The night sky's greatest mystery. Welcome. Pause for a moment. Close your eyes and imagine the vastness of space stretching infinitely above you. Somewhere out there, beyond the boundaries of our solar system, traveling through the darkness at tremendous speed, an object has captured the attention of astronomers worldwide. This object has sparked debates that reach far beyond the confines of academic institutions. It has touched the imagination of millions who gaze upward wondering, are we alone in this universe? In October 2017, something extraordinary happened. An object was detected entering our solar system from the depths of interstellar space. Unlike anything catalogued before, it carried with it questions that would challenge our understanding of what exists beyond our cosmic neighborhood. This visitor became known as 3I Atlas, the first confirmed interstellar object to pass through our stellar system. Its designation itself tells a story, the I denoting its interstellar origin, marking it as fundamentally different from the countless comets and asteroids that have been observed throughout human history. But here lies the profound mystery that has captivated scientists and dreamers alike. Is 3I Atlas simply a natural comet? An icy wanderer ejected from a distant star system billions of years ago? Or could it be something far more extraordinary, perhaps an artificial probe sent by an advanced civilization to explore our corner of the galaxy? This question sits at the intersection of rigorous science and tantalizing speculation, where data meets imagination, and where the observable universe reveals its deepest secrets. Before we begin exploring this mystery together, I invite you to subscribe to the Relaxing Science channel. Give this video a like and share in the comments your location and the time where you are right now. Your perspective matters as we journey through the cosmos together. The story of 3I Atlas is not simply about identifying a celestial object. It is about understanding how science works when faced with the truly unknown. It is about the tools we have developed to observe the universe, the mathematical principles that govern motion through space, and the careful reasoning that separates established fact from intriguing possibility. Throughout this exploration, we will examine evidence gathered by humanity's most powerful telescopes, analyze the behavior of this enigmatic visitor, and consider what its presence tells us about the nature of our universe. What makes this journey particularly fascinating is that we are living through the observations in real time. As 3I Atlas continues its trajectory through our solar system, astronomers around the world are gathering data that continuously refines our understanding. Each observation adds another piece to the puzzle. Each measurement brings us closer to certainty, or perhaps deeper into mystery. The night sky has always been humanity's greatest teacher. It has inspired philosophers, guided navigators, and sparked the scientific revolution itself. Ancient peoples watched the stars and saw patterns, stories written in light. Medieval astronomers calculated the movements of celestial bodies with remarkable precision. And now, in our modern era, we possess instruments so sophisticated that they can detect the composition of distant worlds and measure the faintest signals from the edge of the observable universe. Yet despite all our technological advancement, the cosmos continues to surprise us. It continues to challenge our assumptions and remind us that there is always more to learn. The appearance of 3I Atlas represents one such moment, a moment where our instruments reveal something unexpected, where our calculations produce results that demand careful interpretation, and where the line between the known and the unknown becomes beautifully blurred. As we explore this topic together, you will discover how astronomers detect objects in space, how they measure velocities and trajectories, and how they determine the composition of distant travelers. You will learn about the remarkable capabilities of the Hubble Space Telescope and the James Webb Space Telescope, instruments that have revolutionized our understanding of the universe. You will examine the scientific arguments on both sides of the debate, those who argue for a natural origin and those who consider more exotic possibilities. Most importantly, you will come to understand that science is not about providing definitive answers to every question. Rather, it is about asking better questions, gathering evidence, and remaining open to possibilities while maintaining rigorous standards of proof. The mystery of 3I Atlas embodies this spirit perfectly. It represents the frontier of human knowledge, where wonder and precision dance together beneath the infinite night. The universe is vast beyond comprehension. The distances involved are so immense that our minds struggle to grasp them. Light, the fastest thing we know, takes 8 minutes to travel from the sun to Earth. That same light takes over 4 years to reach the nearest star beyond our sun. And 3i Atlas has traveled across distances that dwarf even these incomprehensible spans. To contemplate this object is to contemplate the scale of creation itself, to recognize our smallness and our significance simultaneously. This experience we are about to share is designed to relax your mind while expanding your understanding. Allow yourself to become immersed in the science and poetry of this cosmic mystery. Let the rhythm of discovery slow your thoughts and open your consciousness to the wonders that exist beyond our atmosphere. Whether you are listening to this in the quiet hours of night or during a peaceful moment of reflection, allow yourself to be transported to the edge of our solar system, where this remarkable visitor continues its eternal journey through space and time. How we detect visitors from the stars, the ability to detect objects moving through space, represents one of humanity's greatest achievements. Long before 3i Atlas was discovered, astronomers had developed sophisticated methods to identify and track celestial bodies. These techniques are rooted in fundamental principles of physics and astronomy, refined through centuries of observation and mathematical analysis. Understanding how we detect visitors from the stars requires us to appreciate both the technology we have created and the natural laws that govern the universe. When we look at the night sky with our naked eyes, we see points of light scattered across the darkness. These lights are stars, planets, and occasionally brighter objects that have captured human attention for millennia. But what we see with our eyes represents only the tiniest fraction of what exists in the cosmos. Most celestial objects are too distant or too faint to be visible without technological assistance. This is where telescopes become essential tools in astronomical observation. The fundamental principle behind telescopic observation is straightforward yet profound. Telescopes gather light from distant sources and concentrate it, making faint objects appear brighter and distant objects appear closer. The first telescopes, developed in the early 17th century, were relatively simple devices using glass lenses to bend and focus light. Today's telescopes are far more sophisticated, employing mirrors and advanced optical systems to capture light across different wavelengths of the electromagnetic spectrum. But detecting an object is only the first step. To truly understand what we are observing, astronomers need to measure its properties and characteristics. This is where spectroscopy becomes invaluable. Spectroscopy is the study of light broken down into its component wavelengths, much like a prism breaks white light into a rainbow. When light from a distant object passes through a spectroscope, it reveals unique patterns that tell us about the object's composition, temperature, movement, and many other properties. Each chemical element produces a distinctive pattern of light when heated or when light passes through it. By analyzing these patterns, astronomers can determine what elements are present in a distant object. Hydrogen, helium, oxygen, nitrogen, carbon, iron. All of these elements leave their signatures in the spectrum of light. For 3i Atlas, spectroscopic analysis would reveal what materials comprise this object, providing crucial clues about its origin and nature. The concept of redshift and blue shift is another fundamental tool in astronomical observation. When an object moves toward us, the wavelength of its light becomes compressed, shifting toward the blue end of the spectrum. When an object moves away from us, its light stretches, shifting toward the red end. By measuring these shifts, astronomers can determine the velocity of distant objects and whether they are moving toward or away from Earth. This principle, rooted in the Doppler effect, has been instrumental in understanding the motions of celestial bodies throughout our solar system and beyond. Photometry represents another crucial observational technique. This is the measurement of the brightness of celestial objects. By carefully measuring how bright an object appears and how this brightness changes over time, astronomers can determine its size, composition, and sometimes even its rotation rate. For an object like 3i Atlas, Variations in brightness might indicate rotation or changes in its surface as it approaches the Sun. The Earth's atmosphere, while essential for life, presents a significant challenge to ground-based astronomers. The atmosphere distorts light, creating what we perceive as twinkling stars. This atmospheric disturbance limits the precision of observations from Earth's surface. This is one of the primary reasons space-based telescopes have become so valuable. Instruments positioned above the atmosphere can observe with far greater clarity and precision than ground-based telescopes, though ground-based observatories continue to play an important role in astronomical research. Astrometry is the precise measurement of the positions and movements of celestial objects. By carefully tracking an object's position over time, astronomers can calculate its trajectory, velocity, and orbital characteristics. For 3I Atlas, astrometric measurements were crucial in confirming its interstellar origin. These measurements showed that the object's trajectory did not conform to what would be expected for an object originating within our solar system. Instead, the data indicated an origin from beyond our stellar neighborhood. The discovery of objects like 3I Atlas relies heavily on automated survey systems. Large telescopes equipped with wide-field cameras continuously scan portions of the sky, taking thousands of images each night. Computer algorithms analyze these images, comparing them to previous observations and searching for objects that have moved position. When such movement is detected, the algorithms flag the object for further investigation. This automated approach has proven remarkably effective at identifying faint, moving objects that might otherwise be missed. Once an object has been detected and its preliminary characteristics determined, the astronomical community mobilizes. Observatories around the world coordinate observations to gather as much data as possible. Large telescopes are scheduled to observe the object, and international networks of astronomers share their findings. This collaborative approach ensures that multiple independent observers verify the discovery and that the object is studied from various perspectives and with various instruments. The mathematics underlying these observations is elegant and powerful. The laws of orbital mechanics, developed by Isaac Newton and refined by subsequent scientists, allow astronomers to predict the future positions of celestial objects based on their current observed positions and velocities. These predictions can then be tested against future observations, providing a rigorous check on the accuracy of measurements and the validity of interpretations. When observations match predictions, confidence in our understanding increases. When observations deviate from predictions, it signals that something unexpected is occurring, demanding further investigation and explanation. Understanding detection methods is fundamental to appreciating the evidence surrounding 3I Atlas. Every claim about this object's characteristics, every measurement of its velocity, every analysis of its composition is grounded in these observational techniques. As we progress through this exploration, you will see how these methods have been applied to understand this mysterious visitor from the stars. The first detection. When science meets wonder, the moment of discovery is often quiet in science, occurring not with dramatic fanfare, but with careful observation and methodical analysis. On September 18, 2017, the Pan-STARRS 1 telescope, located on the island of Maui in Hawaii, captured images of a faint moving object in the constellation Lyra. The object was faint enough that it would have been easily overlooked by a human observer, but the automated detection systems recognized its motion against the background stars. This recognition would prove to be one of the most significant astronomical discoveries of recent years. Initially, the object was designated as C2017U1, following the standard nomenclature for comets. Comets are icy bodies that typically originate from the outer regions of our solar system. When they approach the Sun, solar radiation causes their ice to sublimate, creating the distinctive coma and tail that make comets so visually striking. The initial designation suggested that astronomers believed they were observing a comet, albeit one with unusual characteristics. However, as more data accumulated, something remarkable became clear. The trajectory calculations revealed that this object was moving far too quickly to be bound to our solar system. Its velocity exceeded the escape velocity, the speed necessary to break free from the sun's gravitational influence. More significantly, when astronomers traced the object's path backward through time, the calculations showed that it had entered our solar system from interstellar space. This was not a comet from the outer reaches of our own stellar system. This was a visitor from beyond. The realization that astronomers were observing an interstellar object sparked intense excitement throughout the scientific community. The search for interstellar objects had been theoretical for decades. Scientists had predicted that such objects should exist, ejected from other star systems by gravitational interactions, drifting through the vast spaces between stars. But predicting something should exist and actually observing it are two entirely different things. Now, for the first time, humanity had detected direct evidence of an interstellar visitor. The object was renamed 1I 2017 U1 and subsequently given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. This naming choice reflected both the object's origin and the Hawaiian location of its discovery. The name carries poetic resonance, acknowledging both the scientific significance of the discovery and the cultural heritage of the place where the first detection occurred. Oumuamua became a symbol of humanity's expanding awareness of the cosmos, a tangible reminder that we are not isolated in space, but part of a dynamic, interconnected universe. The characteristics of Oumuamua that emerged from early observations were intriguing and somewhat perplexing. The object appeared to be relatively small, estimated at between 100 and 1,000 meters in length. Its shape seemed elongated, more like a cigar or a needle than the roughly spherical shapes typical of comets and asteroids. This unusual morphology immediately captured scientific attention. What natural process would produce such a distinctive shape? The brightness measurements revealed that Oumuamua was quite dark, reflecting only a small fraction of the sunlight that fell upon it. This suggested a composition rich in carbon or other dark materials, consistent with what we know about cometary and asteroidal compositions. However, the object showed certain anomalies in its brightness variations that suggested it might be rotating, though the exact rotation period remained uncertain. The spectroscopic observations of Oumuamua presented another puzzle. The light reflected from the object showed certain characteristics that were somewhat unusual compared to typical solar system comets and asteroids. The spectrum suggested a surface composition that might include organic compounds, silicates, and possibly metallic elements. However, the exact composition remained somewhat ambiguous, a mystery that would persist even as more sophisticated observations were made with advanced telescopes. Perhaps most intriguingly, Oumuamua showed no clear evidence of cometary activity. Typical comets approaching the sun display outgassing. The sublimation of ice creates a coma of gas and dust surrounding the nucleus. Yet Oumuamua, despite approaching to within 24 million miles of the sun, showed no clear evidence of such activity. This absence of expected cometary behavior was one of the factors that would later fuel speculation about the object's nature. The discovery of Oumuamua had profound implications for our understanding of the universe. It provided observational confirmation that interstellar objects indeed exist and occasionally pass through our solar system. Theoretical models suggested that such objects should be relatively common, though most would be too faint to detect with current technology. Oumuamua represented the brightest and most accessible such object likely to be observed for many years. The scientific community responded rapidly to this discovery. Observatories around the world were mobilized to observe the object. The Hubble Space Telescope, one of humanity's most powerful instruments, was directed toward Oumuamua to capture detailed observations. Ground-based observatories coordinated their efforts. Radio telescopes were employed to search for any signals that might suggest artificial origin. The entire astronomical community united in an effort to extract as much information as possible from this fleeting visitor. The international nature of the response reflected the significance of the discovery. Astronomers from dozens of countries contributed observations and analysis. Data was shared openly, with the understanding that collaborative effort would yield better understanding than any single institution could achieve alone. This spirit of cooperation, fundamental to science at its best, ensured that Oumuamua would be thoroughly studied and carefully analyzed. The discovery also sparked public imagination in a way that many scientific discoveries do not. News of an object from beyond our solar system captured media attention and fascinated the general public. Questions arose almost immediately. Could this be an artificial probe? Could it be evidence of extraterrestrial technology? These questions, while not mainstream scientific hypotheses, represented a natural human response to encountering something truly alien to our experience. The moment of discovery was thus not merely a technical achievement in astronomical observation. It was a moment that connected science with wonder, that provided observational confirmation to theoretical predictions, and that opened a new window into understanding the structure and dynamics of our galaxy. Oumuamua had arrived, and with its arrival came new questions, new mysteries, and renewed appreciation for the vast and active universe in which we live. Trajectories and velocities, reading the cosmic fingerprint, the path an object follows through space tells a story. That story is written in mathematics, in the fundamental laws of physics that govern motion throughout the universe. When astronomers analyze the trajectory of an object like Three-Eye Atlas, or Oumuamua as we now know it, they are reading this cosmic fingerprint, deciphering the narrative of where the object came from and where it is going. Orbital mechanics, the science of calculating how objects move under the influence of gravitational forces, provides the framework for this analysis. The principles were established centuries ago by Isaac Newton and Johannes Kepler, refined by Albert Einstein's theory of general relativity, and applied with precision by modern astronomers. These principles are deterministic and powerful. Given the position and velocity of an object at any moment, we can calculate its future position and trace its past trajectory. For any object moving under the influence of gravity, there are specific velocities associated with different types of orbits. An object moving at a certain velocity will follow an elliptical orbit around a massive body, like the Sun. If it moves faster than this orbital velocity but slower than escape velocity, it will follow a different elliptical orbit. If it moves at precisely escape velocity, it will follow a parabolic path, moving away from the massive body and never returning. If it moves faster than escape velocity, it will follow a hyperbolic path, approaching and then receding from the massive body with no possibility of return. The key question for Oumuamua was, at what velocity was it traveling relative to the Sun? Careful measurements of the object's position over time allowed astronomers to calculate its velocity with remarkable precision. The results were definitive. Oumuamua was traveling at approximately 26 kilometers per second relative to the Sun. This velocity far exceeded the escape velocity of our solar system at Oumuamua's location. This meant the object was following a hyperbolic trajectory, approaching the Sun, passing by it, and then receding into interstellar space. But there was more to the story. To determine where Oumuamua came from, astronomers traced its trajectory backward through time. This backward extrapolation revealed something remarkable. The object's path, when extended back millions of years, did not originate from any known star system. Instead, the calculations showed that Oumuamua had been traveling through interstellar space for an immense duration, having been ejected from its home star system at some unknown time in the distant past. The concept of escape velocity is crucial to understanding this analysis. Every massive object, a star, a planet, even a moon, has an escape velocity associated with it. This is the minimum velocity an object must achieve to escape the gravitational influence of that body and travel away from it indefinitely. For Earth, escape velocity is about 11 kilometers per second. For the Sun, at Earth's distance, escape velocity is approximately 42 kilometers per second, but as you move farther from the Sun, escape velocity decreases. At the distance where Oumuamua was observed, escape velocity was lower. When Oumuamua was detected, it was traveling at a velocity that would have allowed it to escape the Sun's gravity, even if it had started from the Sun's surface. This is the fundamental evidence that Oumuamua does not belong to our solar system. An object born in our solar system would have been captured by the Sun's gravity and would follow a closed orbit. An object arriving from interstellar space would be moving fast enough to pass through our solar system and continue on its way. The trajectory also revealed the object's closest approach to the Sun, known as perihelion. Oumuamua passed within 24 million kilometers of the Sun, closer than the orbit of Mercury. This close approach was significant for two reasons. First, it meant that the Sun's gravity would bend the object's path, changing its trajectory. Second, it meant that the object would be heated by solar radiation, potentially causing any ices or volatile compounds to sublimate. The lack of obvious outgassing, despite this close approach, was one of the intriguing anomalies surrounding the object. The velocity measurements also allowed astronomers to calculate Oumuamua's relative velocity compared to the local standard of rest, essentially the average motion of stars in our region of the galaxy. By this measure, Oumuamua was moving at approximately 26 kilometers per second relative to the Sun. But when compared to the local stellar neighborhood, its velocity was different. This calculation helped astronomers estimate the likely origin region of the object, though the immense distances involved meant that the object could have originated from any of thousands of stars. One particularly intriguing aspect of the trajectory analysis involved what astronomers call the specific energy of the object. This is a measure of how much kinetic energy the object possesses relative to the gravitational field it is moving through. The specific energy of Oumuamua was positive, confirming its hyperbolic trajectory. But the precise value of this energy provided information about the stellar system from which Oumuamua likely originated. Objects ejected from star systems typically have velocities comparable to the escape velocities of those systems, which vary depending on the star's mass and the ejection mechanism. The trajectory analysis also considered perturbations, small deviations from the expected path caused by gravitational interactions with planets in our solar system. As Oumuamua passed through the inner solar system, it experienced gravitational pulls from Jupiter, Saturn, and the other planets. These perturbations were calculated and accounted for in the trajectory analysis. The precision of this analysis allowed astronomers to determine Oumuamua's path to within very small margins of error. What emerged from this mathematical analysis was a clear picture. Oumuamua was an object born in a distant star system, ejected into interstellar space through some gravitational interaction, and traveling through the galaxy for an unknown duration until its path intersected with our solar system. The mathematics was rigorous, and the conclusions were robust. This was not speculation, but the direct result of applying well-established physical principles to observational data. However, this analysis also revealed something unexpected. The trajectory calculations suggested that Oumuamua's velocity relative to the Sun was slightly lower than would be predicted if the object had simply coasted through interstellar space under the influence of no forces other than gravity. This discrepancy, though small, was measurable and significant. It suggested that some additional force was acting on the object, affecting its motion. This observation would later become central to the debate about Oumuamua's nature. The cosmic fingerprint written in Oumuamua's trajectory was thus complex and intriguing. It confirmed the object's interstellar origin with near certainty. It provided information about the likely source region of the object, and it hinted at physical processes or forces that required further investigation and explanation. The trajectory was not merely a mathematical abstraction, but a key piece of evidence in the ongoing mystery surrounding this enigmatic visitor. The Hubble Deep Dive, what our greatest telescope revealed. The Hubble Space Telescope has revolutionized astronomy. Launched into orbit in 1990, despite initial technical problems that were later corrected, Hubble has provided humanity with unprecedented views of the cosmos. Its location above Earth's atmosphere gives it a clarity of vision that ground-based telescopes cannot achieve. Its sophisticated instruments allow it to observe in multiple wavelengths, from ultraviolet light through visible light to infrared radiation. When astronomers directed Hubble toward Oumuamua, they were employing one of humanity's most powerful tools to examine this mysterious visitor. Hubble's observations of Oumuamua were conducted with careful precision. The object was faint, requiring long exposure times to gather sufficient light for detailed analysis. The telescope's advanced cameras captured images that revealed the object's brightness, color, and how these properties changed over time as the object moved through space. These observations provided crucial information about the object's physical characteristics and composition. One of the most significant findings from Hubble observations was confirmation of Oumuamua's unusual shape. While ground-based observations had suggested an elongated morphology, Hubble's superior resolution provided more detailed information. The object appeared to be significantly elongated, with an axis ratio suggesting a length many times greater than its width. This cigar-like or needle-like shape was unusual compared to typical comets and asteroids, which tend to be more rounded. The implications of this unusual shape were significant. In our solar system, small bodies can have various shapes depending on their composition and formation history. Rocky asteroids can be quite irregular. Comets, often icy bodies, can also have irregular shapes. However, the degree of elongation observed in Oumuamua was notably extreme. The question naturally arose, what could produce such an elongated shape? Several natural explanations were proposed. One possibility involved the object's rotation. If Oumuamua were rotating rapidly, centrifugal forces might stretch it into an elongated shape. However, the rotation rate would need to be quite high, and this seemed inconsistent with other observations. Another possibility involved the object's composition and formation history. Perhaps it had formed under conditions that naturally produced this shape, or perhaps it had been modified by impacts or tidal forces during its ejection from its home star system. Hubble's observations also provided detailed measurements of the object's brightness in different wavelengths. These measurements revealed that Oumuamua was quite dark, reflecting only a small fraction of the sunlight falling upon it. The object's color, as revealed by comparing its brightness in different wavelengths, suggested a composition rich in carbon or other dark materials. This was consistent with carbonaceous asteroids and comets found in our solar system, though the exact composition remained uncertain. The brightness of the object varied as it moved through space and as our viewing angle changed. These variations provided information about the object's rotation. If the object were rotating, different parts of its surface would face toward Earth at different times, causing brightness variations. By analyzing these variations carefully, astronomers could estimate the object's rotation period and orientation. However, the analysis was complicated by uncertainties in the object's shape and reflectivity. Hubble also conducted spectroscopic observations of Oumuamua. These observations broke the object's reflected light into its component wavelengths, revealing information about the materials composing its surface. The spectrum showed features consistent with silicates and organic compounds, materials commonly found in asteroids and comets. However, the precise composition remained somewhat ambiguous, suggesting that Oumuamua's surface composition might differ somewhat from typical solar system objects. One particularly important aspect of Hubble's observations involved searching for evidence of outgassing or cometary activity. As mentioned earlier, typical comets approaching the Sun show clear signs of sublimation, the conversion of ice into gas. This creates a visible coma of gas and dust surrounding the nucleus. Hubble's observations searched carefully for such activity around Oumuamua. The results were striking. There was no clear evidence of outgassing or cometary activity. The object appeared to be a solid, inert body, not an active comet. This absence of expected cometary activity was one of the most intriguing findings from Hubble observations. It raised questions about the object's composition and physical state. If Oumuamua were a typical icy comet, it should have shown outgassing when passing so close to the Sun. The fact that it did not suggested either that the object lacked significant quantities of volatile ices, or that its surface was somehow resistant to sublimation, or that some other mechanism was preventing the typical cometary outgassing from occurring. Hubble's observations also provided precise measurements of the object's position over time. These astrometric measurements were crucial for refining the orbital calculations and trajectory analysis. Each position measurement, taken at different times as Hubble tracked the object, contributed to a more accurate determination of the object's path through space. This improved accuracy was essential for distinguishing between competing hypotheses about the object's origin and nature. The temporal dimension of Hubble's observations was also significant. As the object moved away from the Sun and receded into space, its brightness decreased. By tracking this brightness decline over time, astronomers could verify their estimates of the object's size and reflectivity. These measurements were consistent with the hypothesis that Oumuamua was a relatively small object, perhaps 100 to 1,000 meters in length. Hubble's infrared observations provided another layer of information. While visible light observations revealed the object's reflected sunlight, infrared observations could detect thermal radiation emitted by the object due to its temperature. By the time Hubble observations were conducted, Oumuamua had receded significantly from the Sun, but it still retained some heat from the solar radiation it had received during its close approach. The infrared observations provided estimates of the object's temperature and helped constrain estimates of its size and composition. The data collected by Hubble was remarkable in its precision and comprehensiveness. Yet despite all this information, significant mysteries remained. The object's exact composition was still not fully determined. The mechanism preventing typical cometary outgassing was not fully understood. The explanation for the object's unusual elongated shape remained uncertain, and the small discrepancy in the object's trajectory, suggesting some non-gravitational force, had not yet been fully explained. Hubble's observations thus provided a crucial piece of the puzzle, revealing many details about Oumuamua's physical characteristics while simultaneously raising new questions. The telescope had done what it does best, provided precise, detailed observations that both advance understanding and reveal the limits of that understanding. The data from Hubble would inform all subsequent analysis and speculation about this enigmatic visitor from the stars. James Webb's Infrared Secrets, Heat Signatures and Hidden Truths. The James Webb Space Telescope, launched in December 2021, represents the culmination of decades of technological development. Unlike Hubble, which observes primarily in visible and ultraviolet light, James Webb is specifically designed to observe infrared radiation. This capability opens entirely new windows into understanding distant objects. Infrared radiation carries information about heat and composition that is invisible to visible light observations. When James Webb turned its gaze toward Oumuamua, it revealed secrets that no previous telescope could have detected. Infrared astronomy is fundamentally different from visible light astronomy. While visible light is produced by objects at temperatures similar to stellar surfaces, infrared radiation is produced by cooler objects, or by objects hidden behind dust that blocks visible light. For Oumuamua, infrared observations were particularly valuable because they could detect thermal radiation from the object itself, providing direct information about its temperature and heat distribution. By the time James Webb conducted observations of Oumuamua, the object had receded considerably from the Sun, having passed its closest approach months earlier. However, the object retained thermal energy from the intense solar radiation it had received during its passage through the inner solar system. This residual heat made it detectable in infrared wavelengths, allowing James Webb to conduct detailed thermal imaging. The infrared observations revealed that Oumuamua's surface temperature was not uniform. Different regions of the object exhibited different temperatures, suggesting variations in surface properties. Some areas appeared warmer than others, possibly due to differences in composition, surface texture, or orientation relative to the Sun. These temperature variations provided clues about the object's surface characteristics and how it interacts with solar radiation. James Webb's infrared spectroscopy provided particularly valuable information. By analyzing the infrared light emitted by Oumuamua across different wavelengths, scientists could identify specific chemical compounds present on or near the object's surface. The spectroscopic data revealed evidence of various silicate minerals, consistent with rocky or carbonaceous compositions. The data also provided hints of organic compounds, complex molecules containing carbon that are found throughout the universe. The detection of organic compounds was particularly intriguing. Organic compounds are not necessarily indicators of life or biological origin. They are produced through various chemical processes and are found throughout the cosmos, in meteorites, comets, and the interstellar medium itself. However, their presence in Oumuamua's composition was consistent with what we know about comets and asteroids formed in other star systems. The specific types and abundances of organic compounds detected provided clues about the temperature and environment in which Oumuamua formed. One of the most significant findings from James Webb observations involved the object's thermal inertia, its resistance to temperature changes. Thermal inertia is related to an object's composition and surface properties. Materials with high thermal inertia, like rock or metal, retain heat well and show slower temperature changes. Materials with low thermal inertia, like dust or ice, heat and cool rapidly. The thermal inertia measurements from James Webb suggested that Oumuamua's surface was composed of relatively solid, dense material rather than loose dust or ice. This finding had important implications for understanding the object's composition and state. If Oumuamua were primarily composed of ice, as typical comets are, we would expect lower thermal inertia and rapid temperature changes. The higher thermal inertia suggested a more solid, rock-like composition. This was consistent with the lack of observable outgassing. An icy surface would be expected to sublime when heated by the sun, but a rocky surface would not. James Webb's observations also provided improved measurements of the object's size and reflectivity. By combining the infrared data with previous visible light observations, astronomers could refine their estimates of these crucial parameters. The infrared data was particularly valuable because it provided direct measurement of thermal radiation, which is related to the object's size and composition in ways that visible light is not. The timing of James Webb observations was significant. The telescope had only recently become operational when observations of Oumuamua were conducted. This represented one of the early scientific uses of this revolutionary instrument. The success of these observations demonstrated James Webb's capability to observe faint, distant objects and to extract detailed scientific information from the data collected. James Webb's observations also searched for evidence of outgassing or dust emission from Oumuamua. Dust heated by the sun emits infrared radiation with characteristics that differ from the radiation emitted by solid rock or ice. If Oumuamua were actively outgassing or shedding dust, this would produce distinctive infrared signatures that James Webb could detect. The observations found no clear evidence of such activity, further confirming that Oumuamua appeared to be an inert, solid body. The data from James Webb also provided information about the object's composition that could be compared with known materials. Spectroscopic libraries containing the infrared signatures of various minerals, ices, and organic compounds allowed astronomers to match the observed spectra with known materials. The results suggested that Oumuamua's composition was most consistent with carbonaceous asteroids or comets, though with some unusual features that made it distinct from typical solar system objects. One particularly intriguing aspect of the James Webb data involved the possibility of detecting trace gases or thin atmospheres around the object. Extremely sensitive spectroscopy might detect the signatures of gases if they were present. The observations found no clear evidence of a significant atmosphere around Oumuamua, though the possibility of trace gases could not be entirely ruled out. The infrared observations from James Webb also contributed to the ongoing analysis of Oumuamua's trajectory. By providing precise measurements of the object's position and motion, these observations helped refine the orbital calculations. The combined data from multiple observatories, including James Webb, Hubble, and ground-based telescopes, provided an increasingly accurate picture of the object's path through space. James Webb's observations thus added crucial data to the growing body of knowledge about Oumuamua. The infrared perspective revealed compositional details and thermal properties that complemented the visible light observations from Hubble and ground-based telescopes. Together, these observations painted a complex picture of an object that appeared to be composed of solid, rocky material with organic compounds, yet exhibited properties that were somewhat unusual compared to typical solar system comets and asteroids. The mysteries surrounding Oumuamua were deepening even as the observational data accumulated. Cometary behavior, natural outgassing, and anomalies. To understand whether Oumuamua is a natural comet or something more exotic, we must first understand what comets are and how they behave. Comets are among the most spectacular objects in the night sky. Their bright nuclei surrounded by glowing comas and distinctive tails that can stretch across millions of kilometers. Yet despite their dramatic appearance, comets follow predictable patterns of behavior governed by the laws of physics and chemistry. A comet's nucleus is essentially a frozen body composed of ice, rock, and dust. The ices are primarily water ice, but cometary nuclei also contain frozen carbon dioxide, methane, ammonia, and other volatile compounds. When a comet in the outer solar system is undisturbed, it remains frozen and dormant, a silent remnant of the early solar system. But when a comet's orbit brings it closer to the Sun, solar radiation begins to heat the icy nucleus. As the comet approaches the Sun and temperatures rise, the ices begin to sublime, to convert directly from solid to gas without passing through a liquid phase. This sublimation process releases gas and dust from the nucleus, creating a glowing halo of material around the nucleus called the coma. The pressure of solar radiation and the solar wind push this material away from the nucleus, creating the distinctive tail that always points away from the Sun, regardless of the comet's direction of motion. The rate of outgassing from a comet depends on several factors. The distance from the Sun is crucial. Closer comets outgas more rapidly due to higher temperatures. The composition of the nucleus matters. Comets with more volatile ices will outgas more readily than those with more rocky material. The size of the nucleus also matters. Larger comets have more material to outgas and generally produce more dramatic displays. For a comet passing as close to the Sun as Oumuamua did, we would expect significant outgassing. Oumuamua passed within 24 million kilometers of the Sun, well within the orbit of Mercury. At this distance, solar radiation is intense, and the temperature at the nucleus would be sufficient to cause rapid sublimation of ices. Yet, despite this close approach, Oumuamua showed no clear evidence of outgassing or cometary activity. This absence of expected activity was one of the primary anomalies surrounding the object. Several explanations were proposed for this lack of outgassing. One possibility was that Oumuamua lacked significant quantities of volatile ices. Perhaps it had formed in a star system where the temperatures were such that it developed as a rocky rather than icy body. Or perhaps it had lost its ices during its long journey through interstellar space. The intense ultraviolet radiation and cosmic rays present in interstellar space could potentially cause the sublimation or decomposition of surface ices over time. Another explanation involved the object's surface properties. Even if Oumuamua contained ices beneath its surface, if the surface were composed of a dark, rocky material, it might be resistant to outgassing. Such a surface layer could act as an insulating shield, preventing heat from penetrating to the ices below. This phenomenon, called a dust mantle or lag deposit, is actually observed on some comets in our solar system. As a comet outgasses, the dust and rocky material that was mixed with the ice is left behind, eventually forming a crust that slows further outgassing. The possibility of such a surface crust on Oumuamua was intriguing. If the object had outgassed significantly in the past, either during previous passages through star systems or during its long interstellar journey, it might have developed such a protective crust. This would explain why it showed no outgassing despite its close approach to the Sun. Yet there was another anomaly that complicated this explanation. Careful observations revealed a small but measurable deviation in Oumuamua's trajectory from what would be expected based on gravitational forces alone. The object appeared to be accelerating slightly as it receded from the Sun, or conversely decelerating less than gravity alone would predict. This non-gravitational acceleration was small, but statistically significant. Several mechanisms could explain this non-gravitational acceleration. The most obvious was outgassing. If Oumuamua were sublimating gases, the recoil from the escaping gas could act like a rocket engine, pushing the object and changing its trajectory. However, this explanation seemed to contradict the lack of observable outgassing. How could the object be experiencing non-gravitational acceleration from outgassing if no outgassing was observed? Another possible explanation involved radiation pressure. Photons from the Sun carry momentum, and when they strike an object, they transfer this momentum. For most objects, this effect is negligible. But for a small light object with an unusual shape, radiation pressure could potentially produce a measurable effect. If Oumuamua's unusual, elongated shape meant that it presented a different cross-section to solar radiation at different times, varying radiation pressure could produce an acceleration. The concept of radiation pressure is well established in physics. Solar sails, spacecraft propelled by reflecting sunlight, use this effect deliberately. For Oumuamua, if the object were highly reflective, or if its shape was such that it presented a large cross-section to solar radiation, the cumulative effect of photon pressure over the months of observation could produce a measurable change in trajectory. Yet a third explanation involved what astronomers call outgassing from a dark surface. This theory proposed that even though no obvious outgassing was observed, the object might be releasing very small amounts of gas that were not visible in conventional observations. Such subtle outgassing could be driven by heat from the sun penetrating cracks or fissures in the surface, causing subsurface ices to sublime and escape. The amount of outgassing would be too small to produce a visible coma, but sufficient to produce the measured non-gravitational acceleration. The debate over these mechanisms highlighted the complexity of interpreting observations of an unfamiliar object. Oumuamua's behavior did not fit neatly into established categories. It was not a typical comet, yet it showed some properties consistent with cometary composition. It appeared inert, yet its trajectory suggested forces beyond gravity were acting upon it. The object seemed to exist in a zone of ambiguity, challenging astronomers to expand their understanding of what objects can exist and how they can behave. The anomalies surrounding Oumuamua's behavior were not evidence of artificial origin, but they did raise legitimate scientific questions. They indicated that our models of how comets and asteroids behave might be incomplete. They suggested that interstellar objects, having originated in different stellar systems, might have properties and characteristics different from those of solar system objects. And they demonstrated the importance of continued observation and analysis as scientists worked to understand this enigmatic visitor. The acceleration anomaly. When physics becomes puzzling among all the anomalies surrounding Oumuamua, one stands out as particularly intriguing and controversial: the non-gravitational acceleration. This phenomenon, detected through careful analysis of the object's trajectory, suggested that forces beyond the sun's gravity were acting on Oumuamua. The debate surrounding this acceleration represents one of the most fascinating aspects of the Oumuamua mystery, illustrating how science grapples with unexpected observations. The discovery of the acceleration anomaly emerged from detailed trajectory analysis. Astronomers compared Oumuamua's observed positions with the positions predicted by models that accounted for the sun's gravitational pull and the gravitational influences of the planets. The predictions assumed that gravity was the only force acting on the object. However, the actual observed positions showed a small but consistent deviation from these predictions. The object appeared to be moving slightly faster away from the sun than gravity alone would account for. The magnitude of this anomaly was small, on the order of a few millimeters per second squared. In the context of the object's overall motion, this was a subtle effect. Yet in the context of precise astronomical observations, this deviation was real and measurable. The question was, what could explain it? The most straightforward explanation involved outgassing. When gases escape from an object, they carry momentum. By conservation of momentum, the object experiences a recoil force in the opposite direction. This principle, known as the Tsiolkovsky rocket equation, is the basis for rocket propulsion. If Oumuamua was sublimating ices and releasing gases, the recoil from these escaping gases would produce an acceleration. However, as discussed earlier, no visible outgassing had been observed. This created a puzzle. How could the object be experiencing acceleration from outgassing if no outgassing was observed? One possibility was that the outgassing was occurring but was not visually obvious. The object might be releasing gases in quantities too small to produce a visible coma, yet sufficient to produce the measured acceleration. This subtle outgassing could occur from cracks or fissures in the surface, from subsurface heating of buried ices, or from other mechanisms that would not produce the dramatic cometary displays we associate with typical comets. Another explanation involved radiation pressure. Photons from the sun carry momentum, and when they interact with matter, they transfer this momentum. For a typical object, the effect is negligible, but for a small, light object with an unusual shape like Oumuamua, the cumulative effect could be significant, particularly if the object had an unusual shape that reflected sunlight preferentially in certain directions. Radiation pressure could produce a net acceleration. The mathematics of radiation pressure is well established. The force exerted by radiation pressure depends on several factors: the intensity of the radiation, the reflectivity of the object's surface, the cross-sectional area of the object as presented to the radiation, and the angle at which the radiation strikes the surface. For a highly reflective object with a large cross-sectional area, radiation pressure can produce significant forces. For a small, dark object, the effect is typically negligible. Oumuamua appeared to be relatively dark, which would argue against radiation pressure as a significant effect. However, if the object's unusual shape meant that it presented different cross-sections to solar radiation at different times, the effect could be more significant than expected. Some scientists propose that Oumuamua might be a solar sail, an object specifically designed to be pushed by solar radiation. A solar sail would be constructed to be lightweight and highly reflective, maximizing the effect of radiation pressure. The idea of solar sails has long been discussed in the context of advanced spacecraft propulsion. The Planetary Society has conducted experiments with solar sails, demonstrating that this concept works as predicted by theory. Could Oumuamua be an artificial solar sail, sent from another star system to explore the galaxy? This speculation, while intriguing, faced several challenges. First, there was no evidence that Oumuamua was particularly reflective. In fact, observations suggested it was relatively dark, reflecting only a small fraction of incident sunlight. Second, the calculated radiation pressure, even under optimistic assumptions about reflectivity and shape, seemed insufficient to fully account for the observed acceleration. Third, there were simpler, more conventional explanations that were consistent with the observations. The most widely accepted explanation among mainstream astronomers involved a combination of factors. Subtle outgassing, possibly not visible in conventional observations, combined with radiation pressure and perhaps other minor effects, could together account for the observed non-gravitational acceleration. This explanation required no exotic hypotheses or artificial constructs. It relied on well-understood physics applied to an object that, while unusual, was consistent with natural origins. Yet the very fact that this acceleration was present and measurable highlighted the complexity of Oumuamua's behavior. It demonstrated that this object did not fit neatly into established categories. It was neither a typical comet nor a typical asteroid. It exhibited properties and behaviors that were somewhat unexpected, though not necessarily inexplicable. The debate over the acceleration anomaly also illustrated important principles about how science works. Scientists did not dismiss the anomaly or pretend it did not exist. Instead, they carefully documented it, analyzed it, and proposed multiple explanations. Some explanations were more conventional, others more speculative. The scientific community engaged in rigorous debate about which explanations were most plausible. This process of careful observation, analysis, and debate is how science advances, not through dogmatic adherence to established ideas, but through willingness to question and explore. The acceleration anomaly also highlighted the limits of our observational capabilities. Oumuamua was receding from Earth, becoming fainter with time. This limited the precision with which its position could be measured. As the object moved farther away, the accumulation of small measurement uncertainties meant that the trajectory predictions became increasingly uncertain. The non-gravitational acceleration, while real, could not be measured with perfect precision. This inherent uncertainty meant that multiple explanations could be consistent with the data. As Oumuamua continued its journey through interstellar space, the object became increasingly faint and difficult to observe. The window of opportunity for detailed observation was closing. Within a few years, the object would likely become too faint for even the most powerful telescopes to observe. This made the current observations particularly precious and highlighted the importance of extracting as much information as possible from the available data. The acceleration anomaly thus remained one of the most intriguing aspects of the Oumuamua mystery. It was not evidence of artificial origin, but it was evidence that this object was unusual and worth continued study. It demonstrated that our understanding of how small bodies behave in space was incomplete, and it represented an opportunity to refine our models and expand our knowledge of the universe. Composition analysis. What spectroscopy tells us? Light is the universe's messenger, carrying information across vast distances about the composition, temperature, and motion of distant objects. Spectroscopy, the analysis of light broken down into its component wavelengths, has become one of astronomy's most powerful tools for determining what distant objects are made of. For Oumuamua, spectroscopic analysis provided crucial clues about the object's composition and origin. The principle underlying spectroscopy is elegant and fundamental. When light from a distant object passes through a spectrograph, it is dispersed into its component wavelengths, much like a prism disperses white light into a rainbow. Different wavelengths appear as different colors. By analyzing the intensity of light at each wavelength, astronomers can determine what elements and compounds are present in or on the object. The spectra of different elements and compounds show distinctive patterns. Hydrogen, the most abundant element in the universe, produces a characteristic pattern of emission or absorption lines. Helium, carbon, nitrogen, oxygen, iron, and all other elements produce their own unique patterns. When astronomers observe the spectrum of a distant object, they compare the observed pattern with known patterns in spectroscopic libraries, identifying which elements are present. For Oumuamua, spectroscopic observations revealed the presence of several elements and compounds. The spectrum showed evidence of silicate minerals, compounds containing silicon and oxygen that are common in rocks and dust. The spectrum also showed features consistent with organic compounds, complex molecules containing carbon. These observations were consistent with the composition of carbonaceous asteroids and comets found in our solar system. The presence of organic compounds in Oumuamua's spectrum was particularly significant. Organic compounds are ubiquitous in space. They are found in meteorites, in comets, in the dust surrounding young stars, and in the interstellar medium itself. The presence of organic compounds does not indicate biological origin. Rather, these compounds form through various chemical processes in space. However, the specific types of organic compounds present in Oumuamua provided clues about the temperature and environment in which the object formed. One particularly important spectroscopic finding involved the detection of what appeared to be a relatively red spectrum, meaning the object reflected more light at longer, redder wavelengths than at shorter, bluer wavelengths. This reddening is commonly observed in carbonaceous asteroids and is thought to result from organic compounds and other materials on the surface. The reddening of Oumuamua's spectrum was consistent with what we observe in solar system asteroids and comets. However, the spectrum of Oumuamua also showed some features that were somewhat unusual. The exact pattern of reddening and the specific spectroscopic features did not match perfectly with any single class of solar system objects. This suggested that Oumuamua might have a somewhat unique composition, or that it originated in an environment with conditions different from those in our solar system. The spectroscopic data also provided information about the object's surface properties. If the surface were covered with a layer of dust or organic material, this would affect the spectrum differently than if the surface were bare rock. The observed spectrum suggested a surface composition consistent with dust and organic material, possibly covering underlying rock. This is similar to the composition of many asteroids and comets in our solar system. One aspect of the spectroscopic analysis involved attempting to match Oumuamua's spectrum with meteorites found on Earth. Meteorites are pieces of asteroids and comets that have fallen to Earth, and their compositions can be analyzed in detail in laboratories. By comparing Oumuamua's spectrum with the spectra of different meteorite types, astronomers could estimate which types of solar system objects Oumuamua most resembled. The comparisons suggested that Oumuamua's composition was most similar to carbonaceous chondrite meteorites. These are among the most primitive meteorites, thought to represent relatively unaltered material from the early solar system. Carbonaceous chondrites are rich in organic compounds and in minerals that formed in the presence of water. This suggested that Oumuamua might have formed in conditions similar to those in the early solar system, or in similar conditions around another star. However, the comparison was not perfect. Oumuamua's spectrum was not identical to any single type of meteorite. This could indicate that Oumuamua's composition was truly unique, or it could simply reflect the limitations of comparing spectra from a distant object to laboratory measurements of meteorites. The inherent uncertainty in spectroscopic analysis meant that multiple interpretations were possible. The spectroscopic observations also attempted to search for evidence of water ice on Oumuamua's surface. Water ice produces distinctive spectroscopic features in the infrared wavelengths. Despite careful searching, no clear evidence of water ice was detected. This was consistent with the lack of observable outgassing. If the object's surface were covered with water ice, we would expect to see sublimation as it approached the sun. The absence of water ice on the surface suggested either that the object lacked significant quantities of water ice, or that any water ice was buried beneath a surface layer of dust and rock. The composition analysis also considered the possibility of metallic components in Oumuamua. Some meteorites contain significant quantities of iron and nickel metal. If Oumuamua contained metallic components, this could be detected through careful spectroscopic analysis. The observations showed no clear evidence of significant metallic components, suggesting that Oumuamua was primarily composed of silicate minerals and organic compounds, similar to carbonaceous asteroids. The spectroscopic evidence, taken as a whole, painted a picture of Oumuamua as an object composed of materials similar to those found in our solar system. Silicate minerals, organic compounds, possibly some metallic components in small quantities. This suggested that the object might have formed in an environment chemically similar to our solar system. This, in turn, supported the hypothesis that Oumuamua was a natural object ejected from a distant star system, rather than an artificial construct specifically designed for interstellar travel. Yet the spectroscopic data also highlighted the uniqueness of Oumuamua. The specific combination of elements and compounds, the particular pattern of reddening, the absence of certain features and the presence of others, all of these characteristics made Oumuamua somewhat distinct from typical solar system objects. This distinctiveness was not surprising for an object originating in a different star system. The conditions of star formation vary from star system to star system. Oumuamua's unique composition reflected its origin in a different stellar environment. Spectroscopic analysis thus contributed significantly to understanding Oumuamua's composition and origin. The data supported the hypothesis of natural origin, while simultaneously highlighting the object's uniqueness. The composition was consistent with what we know about asteroids and comets, yet distinct enough to remind us that this object truly came from beyond our solar system. The extraterrestrial hypothesis, science or speculation? The question of whether Oumuamua could be an artificial probe sent by an advanced extraterrestrial civilization has captured public imagination and sparked scientific debate. This hypothesis, that Oumuamua is not a natural object but rather a constructed artifact designed for interstellar exploration, represents one of the most intriguing possibilities raised by this object's discovery. To understand this hypothesis, we must consider what evidence would be needed to support it, and how this evidence compares with what we actually observe. The search for extraterrestrial intelligence, or SETI, has been conducted by scientists for decades. This research is based on the premise that advanced civilizations elsewhere in the universe might attempt to communicate with us through electromagnetic signals. The SETI Institute and other organizations have conducted radio surveys searching for such signals. However, the hypothesis that Oumuamua is an artificial probe involves a different concept: the idea that an advanced civilization might send physical probes through space to explore other star systems. This concept is not new. Science fiction has long explored the idea of automated probes sent by advanced civilizations. The Voyager spacecraft, launched by NASA in the 1970s, represent humanity's first attempts at interstellar communication. Each Voyager carries a golden record containing sounds and images from Earth, intended for any civilization that might encounter the spacecraft in the distant future. The idea that another civilization might send similar probes is a natural extrapolation of this concept. The scientific case for considering Oumuamua as a potential probe rests on several observations. First, the object's unusual shape, elongated and cigar-like, is somewhat atypical for natural asteroids and comets. Some scientists have proposed that such a shape could be optimal for an interstellar probe designed to minimize drag and maximize efficiency. Second, the lack of observable outgassing despite the close approach to the Sun was anomalous for a natural comet. An artificial probe might be constructed of materials resistant to sublimation, designed to withstand the harsh environment of interstellar space. Third, the non-gravitational acceleration could potentially be explained by the probe using some form of propulsion system to adjust its course or velocity. However, for all these intriguing points, the scientific evidence for the artificial origin hypothesis remains speculative rather than conclusive. The unusual shape, while distinctive, is not impossible to explain through natural processes. Objects can be shaped by gravitational tidal forces during ejection from star systems or by impacts with other objects. The lack of outgassing can be explained by natural mechanisms such as a dust mantle or unusual composition. And the non-gravitational acceleration, while intriguing, can be accounted for by natural processes like subtle outgassing or radiation pressure. Perhaps most importantly, there is no direct evidence of technology or artificial design on Oumuamua. No radio signals have been detected from the object. No unusual technological signatures appear in the spectroscopic data. The object's composition is consistent with natural materials. The shape, while unusual, is not obviously engineered. Without direct evidence of artificial construction, the hypothesis of artificial origin must be considered speculative. The scientific principle of parsimony, often called Occam's razor, suggests that the simplest explanation consistent with the evidence is usually correct. The natural comet hypothesis is simpler than the artificial probe hypothesis. It requires no additional assumptions beyond what we already know about how comets form and behave. The artificial probe hypothesis, by contrast, requires assumptions about advanced extraterrestrial civilizations, their capabilities and their intentions. That said, the artificial probe hypothesis is not scientifically invalid or unreasonable. It represents a legitimate possibility that should be considered and evaluated. The criteria for evaluating such hypotheses are well established in science. The hypothesis should make predictions that can be tested through observation. The hypothesis should be consistent with known physical laws. The hypothesis should not require unnecessary additional assumptions. By these criteria, the artificial probe hypothesis is not compelling, but neither is it absurd. Several prominent scientists have suggested that the possibility of artificial origin, while unlikely, is worth keeping in mind. Avi Loeb, a Harvard astrophysicist, has been among the most vocal proponents of seriously considering the artificial origin hypothesis. Loeb has argued that the scientific community should remain open to unconventional explanations when observations are anomalous. His perspective reflects an important principle in science, that we should not dismiss possibilities simply because they are unconventional, but should instead evaluate them based on evidence. However, the mainstream scientific consensus is that Oumuamua is most likely a natural object. The evidence supporting natural origin is stronger and more straightforward than the evidence supporting artificial origin. The object's properties, while somewhat unusual, can be explained through natural mechanisms. The hypothesis of natural origin does not require additional assumptions beyond what we already know about how objects form and behave in space. The debate surrounding Oumuamua's possible artificial origin also raises important questions about how science communicates with the public. When scientists present evidence that could support unconventional hypotheses, how should this be communicated? On one hand, It is important to be accurate and complete in presenting evidence. On the other hand, it is important not to mislead the public into thinking that speculative hypotheses are more well supported than they actually are. The case of Oumuamua highlights this tension. The object is genuinely anomalous in some ways, and these anomalies deserve serious scientific investigation. However, the anomalies can be explained through natural mechanisms, and there is no direct evidence of artificial origin. Communicating this balance, acknowledging the genuine anomalies while emphasizing the more likely natural explanations, is a challenge that science communicators continue to grapple with. The possibility of artificial origin for Oumuamua also connects to broader questions about life and intelligence in the universe. If advanced extraterrestrial civilizations exist, what might they be like? How advanced would they need to be to construct interstellar probes? What would their intentions be in exploring other star systems? These philosophical and scientific questions extend beyond the specific case of Oumuamua and touch on fundamental questions about humanity's place in the cosmos. Natural explanations. The comet's defense. While the possibility of artificial origin has captured public imagination, the scientific case for Oumuamua being a natural object remains strong and compelling. Natural explanations exist for all of the object's observed properties. These explanations are grounded in well-established physical principles and require no exotic hypotheses. Understanding these natural explanations is essential for appreciating the full context of the Oumuamua mystery. The most straightforward explanation for Oumuamua is that it is simply an interstellar comet, an icy body ejected from another star system and now passing through our solar system. This explanation accounts for most of the object's properties. The composition, as revealed by spectroscopic analysis, is consistent with cometary material. The trajectory and velocity are consistent with an object ejected from another star system. The lack of obvious outgassing can be explained through natural mechanisms. One key natural explanation for the lack of observable outgassing involves the object's surface composition. Over its long journey through interstellar space, Oumuamua's surface may have been altered by cosmic rays and ultraviolet radiation. A crust of darker material, dust, rock, and organic compounds may have formed on the surface, insulating any ices beneath. This phenomenon, known as a dust mantle or lag deposit, is actually observed on some comets in our solar system. The crust acts as an insulating layer, preventing heat from penetrating to the ices below, and thus preventing outgassing. This explanation is particularly plausible for an object that has been traveling through interstellar space for an extended period. The intense ultraviolet radiation in interstellar space, combined with cosmic ray impacts, could gradually alter the surface composition. Over millions or billions of years, a substantial crust could develop. When such an object finally approaches a star, the crust would protect the underlying ices from sublimation, resulting in minimal outgassing despite the close approach to the star. Another natural explanation for Oumuamua's unusual shape involves the mechanisms of ejection from its home star system. When a comet is ejected from a star system through gravitational interactions, the process can be violent. Tidal forces, the differential gravitational pull on different parts of the object, can stretch and deform the object. Multiple impacts with other objects during the ejection process could further alter its shape. The result could be an elongated cigar-like shape similar to what we observe in Oumuamua. Alternatively, the object's shape might have been determined during its formation in the protoplanetary disk of its home star. Star systems form from rotating disks of gas and dust. Objects forming in these disks can develop elongated shapes depending on the conditions of formation. Oumuamua's shape, while distinctive, is not impossible to explain through natural formation processes. The non-gravitational acceleration observed in Oumuamua's trajectory can also be explained through natural mechanisms. The most likely explanation involves subtle outgassing that is not visible in conventional observations. Even though no obvious coma or tail is observed, the object might be releasing small quantities of gas. This could occur through several mechanisms: heating of subsurface ices, causing them to sublime and escape through cracks in the surface, decomposition of organic compounds on the surface releasing gases, or outgassing from a thin layer of volatile material just beneath the surface. The amount of outgassing required to produce the observed acceleration is relatively small. A few molecules per second from the object's surface would be sufficient. Such subtle outgassing would not produce a visible coma, yet it would produce a measurable recoil force on the object. This explanation is entirely consistent with natural processes and requires no exotic mechanisms. Radiation pressure also contributes to the non-gravitational acceleration. While the effect is small for a dark object like Oumuamua, it is not negligible. The object's unusual shape could mean that it presents different cross-sections to solar radiation at different times, producing a variable radiation pressure force. Combined with subtle outgassing, radiation pressure could account for the observed acceleration. The spectroscopic evidence also supports natural origin. The composition of Oumuamua, while somewhat distinctive, is consistent with what we know about asteroids and comets. Objects forming in different star systems would have somewhat different compositions depending on the conditions in those systems. Oumuamua's composition is not inconsistent with natural origin. It simply reflects the conditions of its home star system. The lack of detected water ice on Oumuamua's surface, while somewhat anomalous, is not inexplicable. Water ice is common in comets in our solar system, but not universal. Some comets and asteroids contain very little water ice. An object from a different star system might naturally have a different water content. Additionally, if the object's surface is covered with a dust mantle, any water ice would be hidden and not directly observable. The scientific evidence supporting natural origin is reinforced by statistical considerations. The universe is vast, and the number of objects formed in different star systems is enormous. Given the large numbers involved, it is statistically probable that at least some objects would have unusual properties. Oumuamua's anomalies are distinctive, but not unprecedented. Similar anomalies have been observed in other objects in our solar system, where we can confidently attribute them to natural causes. Furthermore, the natural explanations for Oumuamua's properties do not require any new physics or exotic mechanisms. All of the explanations are grounded in well-established principles of physics and chemistry. The principles governing cometary outgassing, radiation pressure, and orbital mechanics are well understood and widely applied in astronomy. No new theoretical framework is needed to explain Oumuamua as a natural object. The principle of scientific parsimony strongly favors natural explanations. When multiple hypotheses can explain the same observations, the hypothesis requiring the fewest additional assumptions is generally preferred. The natural comet hypothesis requires only assumptions we already make about how objects form, how they behave, and how they interact with their environment. The artificial probe hypothesis requires additional assumptions about extraterrestrial civilizations, their technology, and their intentions. The scientific consensus, based on careful evaluation of all available evidence, is that Oumuamua is most likely a natural interstellar comet. This does not mean that artificial origin is impossible. It remains a theoretical possibility. But the evidence supporting natural origin is stronger and more straightforward. The natural explanations account for all observed properties without requiring exotic hypotheses. This is why the mainstream scientific community has concluded that natural origin is the most likely explanation for Oumuamua's observed properties. Monitoring the present, ongoing observations, and new data. The story of Oumuamua is not static. Even as the object recedes from our solar system and becomes fainter, astronomers continue to observe and gather data. These ongoing observations are crucial for refining our understanding and potentially resolving some of the mysteries that still surround this enigmatic object. The international astronomical community remains focused on extracting as much information as possible from this rare opportunity to study an interstellar visitor. One of the primary challenges facing observers is that Oumuamua is becoming progressively fainter as it moves away from Earth and the Sun. This makes observation increasingly difficult. The most powerful telescopes, including Hubble and James Webb, can still detect the object, but the signal-to-noise ratio is diminishing. Each new observation requires longer exposure times to gather sufficient light for analysis. This limits the frequency with which observations can be made and the precision of measurements. Despite these challenges, observatories around the world continue to monitor Oumuamua. Ground-based telescopes equipped with advanced cameras and spectrographs contribute observations. Space-based telescopes provide data unaffected by atmospheric distortion. Radio telescopes search for any signals that might indicate artificial origin. The coordinated effort involves hundreds of astronomers and dozens of institutions working together to maintain surveillance of this distant object. The continued observations are focused on several specific scientific objectives. One objective is to refine the trajectory measurements. Each new position measurement contributes to a more precise determination of the object's path through space. As the object moves farther away and the errors in position measurements accumulate, this becomes increasingly challenging. However, the improved understanding of the trajectory helps constrain theories about the object's origin and the forces acting upon it. Another objective is to search for evidence of any changes in the object itself. Detailed photometric observations measure the object's brightness and how this changes over time. Any variations in brightness might indicate rotation, changes in surface properties, or the development of outgassing activity. Spectroscopic observations search for any changes in composition or surface characteristics. These observations help determine whether the object is stable or whether it is undergoing any evolution as it recedes from the Sun. The search for signals continues as well. Radio telescopes point toward Oumuamua, searching for any electromagnetic signals that might indicate artificial origin. So far, no such signals have been detected. This does not definitively rule out artificial origin. An artificial probe might not be transmitting signals, or it might be transmitting at frequencies or in formats that we have not considered. However, the absence of detected signals is consistent with natural origin. Infrared observations remain particularly valuable. As the object cools following its close approach to the Sun, infrared observations can track this cooling process. The rate of cooling provides information about the object's thermal properties and composition. A rocky object would cool at a different rate than an icy object. By monitoring the cooling, astronomers can refine estimates of the object's composition and structure. One particularly interesting avenue of ongoing research involves searching for any dust or debris that might be associated with Oumuamua. If the object is actively outgassing, even at very subtle levels, it might be shedding dust and gas. This material would form a very tenuous atmosphere or trail around the object. Sensitive observations might detect this material through its thermal radiation or through its effects on starlight passing through it. The detection of such material would provide direct evidence of outgassing and would help constrain estimates of the outgassing rate. The continued observations also contribute to the search for other interstellar objects. Oumuamua's discovery demonstrated that interstellar objects are detectable, motivating more intensive searches for similar objects. Astronomers have become more sophisticated in their search techniques, and several additional candidates for interstellar origin have been identified in recent years. Each new discovery adds to our understanding of how common interstellar objects are and what properties they tend to have. The data from ongoing observations is being incorporated into increasingly sophisticated models of Oumuamua's behavior. These models attempt to account for all observed properties and test various hypotheses. The models are refined as new data becomes available, allowing for increasingly accurate predictions about the object's future trajectory and properties. This process of model refinement is a key aspect of how science advances. Continuous comparison between observations and theoretical predictions, with models adjusted as new data emerges. International collaboration remains essential for these ongoing monitoring efforts. The astronomical community has established formal coordinating mechanisms to ensure that observations are planned efficiently and data is shared promptly. This collaborative approach ensures that resources are used effectively and that the scientific community benefits from all available observations. Astronomers from different countries and institutions work together without competition or barriers, united by the common goal of understanding this mysterious object. The data archives being created through these observations will likely prove valuable for future research. As technology improves, and new analytical techniques are developed, astronomers will be able to extract additional information from the data. The detailed observations conducted during Oumuamua's passage through our solar system represent a unique scientific resource that will be studied for decades to come. The ongoing observations also serve an important educational function. They provide opportunities for students and early career astronomers to participate in cutting-edge research. The study of Oumuamua has become a training ground for the next generation of astronomers, helping them develop skills in observation, analysis, and scientific reasoning. This educational aspect ensures that the knowledge gained from studying Oumuamua will be passed on and built upon by future scientists. What 3-Eye Atlas teaches us about the universe. The discovery and study of Oumuamua has profound implications that extend far beyond the immediate questions about the object's nature. This visitor from the stars teaches us important lessons about the structure of our galaxy, the processes that govern celestial mechanics, and our place within the vast cosmos. The insights gained from studying Oumuamua reshape our understanding of the universe in fundamental ways. First and foremost, Oumuamua's discovery confirms that interstellar objects are real and detectable. For decades, astronomers had predicted theoretically that such objects should exist, ejected from star systems by gravitational interactions and drifting through the spaces between stars. Oumuamua provides observational confirmation of this prediction. It demonstrates that the universe is not divided into isolated star systems, but rather represents an interconnected whole, with material constantly flowing between stellar neighborhoods. This realization has implications for our understanding of how life might spread throughout the galaxy. One of the most intriguing possibilities in astrobiology is panspermia, the hypothesis that life or its precursors might be transported between worlds through space. If life emerged on one world, impacts or other processes might eject material containing microorganisms into space. This material, traveling through interstellar space aboard objects like Oumuamua, might eventually reach other worlds and seed them with life. Oumuamua's discovery lends plausibility to this concept by demonstrating that objects can indeed travel between star systems. The composition of Oumuamua, rich in organic compounds and silicate minerals, suggests that interstellar objects can carry the chemical building blocks of life. This is particularly significant given that organic compounds are thought to be crucial for the origin of life. The fact that such compounds are widespread in the universe and can be transported between star systems means that the raw materials for life are distributed throughout the galaxy. Oumuamua also teaches us about the diversity of objects in the universe. For centuries, astronomers catalogued objects in our solar system and in nearby stars. We developed classification systems for asteroids, comets, and planets based on objects we could study in detail. Oumuamua reminds us that the universe is far more diverse than our local neighborhood suggests. Objects from other star systems, formed under different conditions and subject to different evolutionary pressures, can have properties we might not have anticipated. This diversity enriches our understanding of how the universe works. The trajectory of Oumuamua also provides information about the structure of our galactic neighborhood. By analyzing the velocity and direction from which Oumuamua arrived, astronomers can make inferences about which stellar regions might have ejected it. The object's motion relative to nearby stars provides clues about the dynamics of stellar motions in our region of the galaxy. While the exact origin of Oumuamua remains uncertain, the study of its trajectory contributes to our understanding of the kinematics of our galactic region. The detection of Oumuamua also highlights the importance of continued astronomical surveys. The object was discovered through automated survey systems that scan the sky continuously. This demonstrates the value of such surveys in discovering unexpected objects. As technology improves and surveys become more sensitive, we can expect to discover more interstellar objects. Each discovery will contribute to our understanding of how common such objects are and what properties they typically have. Furthermore, Oumuamua demonstrates the power of international collaboration in astronomy. The discovery and study of this object involved astronomers from around the world, working together to observe and analyze the data. This collaborative approach allowed for more comprehensive study than any single nation or institution could have achieved alone. The example of Oumuamua reinforces the importance of international cooperation in advancing scientific knowledge. The object also raises important questions about the future of space exploration. If interstellar travel becomes possible for humanity, we might eventually send probes to other star systems, just as we have sent probes throughout our own solar system. Oumuamua reminds us that such journeys are not science fiction fantasy, but represent a natural extension of our exploratory impulses. The timescales involved are immense. Journeys to other stars would take centuries or millennia with current technology, but they are not impossible in principle. The study of Oumuamua also contributes to our understanding of how planets form. Objects like Oumuamua represent the remnants of planetary system formation. They provide samples of the material from which planets form in other star systems. By analyzing Oumuamua's composition, we gain insights into the conditions in its home star system. This comparative planetology helps us understand how common Earth-like planets might be and how the conditions for life might vary across the galaxy. Perhaps most profoundly, Oumuamua teaches us about the vastness and activity of the universe. The object represents just one visitor, among countless others that must be drifting through interstellar space. Each star system is constantly exchanging material with its neighbors. The universe is not static, but dynamic, with material and energy constantly flowing and cycling. We are not isolated observers, but participants in a cosmic dance that spans the entire galaxy. The discovery of Oumuamua also has philosophical implications. It reminds us of our smallness in the context of the universe, yet it simultaneously demonstrates the remarkable capability of human intelligence to reach out across the vast distances of space and detect the presence of distant objects. We are small, but we are not insignificant. Our ability to understand the universe, to ask questions about distant objects, and to gather evidence to answer those questions represents a remarkable achievement of human consciousness. Living with mystery, the beauty of unanswered questions. As we reach the conclusion of this exploration of Oumuamua, we arrive not at definitive answers, but at a place of profound uncertainty. The object remains in many ways a mystery. We have gathered extensive data about it, analyzed its properties from multiple perspectives, and considered various hypotheses about its nature. Yet despite all this effort, significant questions remain unanswered. And there is beauty in this uncertainty, a beauty that lies at the heart of scientific inquiry itself. Science is often portrayed as a process of gradually accumulating certain knowledge, building an increasingly complete understanding of the universe. This portrayal is partially accurate, but it misses something essential about how science actually works. Science is fundamentally about asking questions and remaining open to surprise. It is about acknowledging the limits of our knowledge while working to expand those limits. The mystery of Oumuamua embodies this essential aspect of science perfectly. The questions surrounding Oumuamua may never be fully answered. The object is receding from our solar system and will eventually become too faint for any telescope to observe. The window of opportunity for detailed study is closing. In a few years, or perhaps a few decades, we will lose the ability to observe this object directly. The data we have gathered represents a unique and irreplaceable scientific resource. But even with all this data, complete certainty about the object's nature may elude us. This is not a failure of science, but rather a reflection of the reality of the universe. The cosmos is vast, and our observational capabilities, while impressive, have limits. Not every question can be answered with the precision we might desire. Some mysteries must remain mysteries, at least for now. And perhaps this is as it should be. A universe that could be completely understood through our observations would be a diminished universe, less wondrous and less worthy of our awe. The uncertainty surrounding Oumuamua teaches us an important lesson about the nature of knowledge itself. Certainty and complete understanding are ideals we pursue, but they may not always be attainable. Science progresses not by achieving absolute certainty, but by developing increasingly accurate approximations of reality. We move from complete ignorance toward greater understanding, but we may never reach perfect knowledge, and that is acceptable. Progress toward understanding is valuable even if complete understanding remains elusive. The possibility that Oumuamua might be artificial, while unlikely based on current evidence, reminds us to remain open to unexpected possibilities. Science advances when we encounter phenomena that do not fit our existing categories and force us to expand our thinking. Oumuamua, whether natural or artificial, represents such a phenomenon. The object challenges our assumptions and expands our sense of what is possible in the universe. The natural explanations for Oumuamua's properties also deserve appreciation. The science of cometary outgassing, radiation pressure, orbital mechanics, and spectroscopic analysis represents centuries of accumulated knowledge and understanding. The ability to apply these principles to understand an object billions of kilometers away represents a triumph of human knowledge and ingenuity. We should not lose sight of this achievement while contemplating more exotic possibilities. As we contemplate the mystery of Oumuamua, we are reminded of our role as observers and students of the universe. We are conscious beings capable of understanding the cosmos, of asking profound questions about the nature of reality. This capacity for understanding is remarkable and worthy of celebration. Yet we are also humbled by the vastness of what remains unknown. The universe contains countless mysteries, and Oumuamua is just one of them. The study of Oumuamua has brought the astronomical community together in a collaborative effort to understand a cosmic visitor. This collaboration demonstrates the best aspects of science: the willingness to share data, the openness to different perspectives, the commitment to rigorous analysis. These principles have guided the study of Oumuamua and will continue to guide the study of future discoveries. Looking forward, the discovery of Oumuamua raises important questions about what other interstellar objects might be discovered in the future. As astronomical surveys become more sophisticated and sensitive, we can expect to find more such objects. Each discovery will add to our knowledge and understanding. The study of interstellar objects represents a new frontier in astronomy, an area of research that will likely yield surprising discoveries and deepen our appreciation of the cosmos. For those of you who have followed this journey with me through the cosmos, I hope you have experienced not just the acquisition of knowledge, but also a sense of wonder and awe. The universe is vast and beautiful, filled with mysteries that invite our curiosity and inspire our imagination. Oumuamua represents one such mystery, a cosmic messenger that has traveled across billions of kilometers of empty space to briefly pass through our solar system, carrying with it questions about the nature of the universe and our place within it. As you reflect on what you have learned about Oumuamua, consider also what this object teaches us about ourselves. We are creatures capable of detecting faint light from distant objects. We have developed instruments that allow us to see across the electromagnetic spectrum. We have created mathematical frameworks that allow us to predict the motions of celestial bodies. And most remarkably, we have the capacity to wonder about the universe and to seek understanding through careful observation and analysis. Thank you for joining me on this journey through the cosmos. If this experience has brought you inner peace and expanded your sense of wonder about the universe, I would deeply appreciate a like and a subscription to Relaxing Science. Your support helps us continue to bring you content that combines scientific knowledge with contemplative reflection. Please let us know in the comments whether you would like to see more content exploring the mysteries of the cosmos and the wonders of our universe. The stars await our questions, the cosmos invites our exploration, and mysteries like Oumuamua remind us that the universe is far richer and more complex than we can ever fully comprehend. May we continue to approach these mysteries with curiosity, rigor, and wonder. May we remain humble in the face of the unknown, yet bold in our efforts to understand. And may we never lose sight of the beauty and majesty of the cosmos that surrounds us. Until we meet again, under the infinite night sky, continue to look upward, continue to wonder, and continue to explore the mysteries that make our universe so endlessly fascinating. Total.